Chapter 7. Is life based on the laws of physics? New laws to be expected in the organism. What I wish to make clear in this last chapter is, in short, that from all we have learnt about the structure of living matter, we must be prepared to find it working in a manner that cannot be reduced to the ordinary laws of physics. And that, not on the ground that there is any new force or whatnot directing the behavior of the single atom within a living organism, but because the construction is different from anything that we have yet tested in the physical laboratory. To put it crudely, an engineer familiar with heat engines only will, after inspecting the construction of an electric motor, be prepared to find it working along principles which he does not yet understand. He finds the copper familiar to him in kettles, used here in the form of long wires wound in coils. The iron familiar to him in levers and bars and steam cylinders is here filling the interior of those coils of the copper wire. He will be convinced that it is the same copper and the same iron, subject to the same laws of nature, and he is right in that. The difference in construction is enough to prepare him for an entirely different way of functioning. He will not suspect that an electric motor is driven by a ghost because it is set spinning by the turn of a switch, without boiler and steam. Reviewing the biological situation. The unfolding of events in the life cycle of an organism exhibits an admirable regularity and orderliness, unrivaled by anything we meet with in inanimate matter. We find it controlled by a supremely well-ordered group of atoms, which represent only a very small fraction of the sum total in every cell. Moreover, from the view we have formed of the mechanism of mutation, we conclude that the dislocation of just a few atoms within the group of governing atoms of the germ cell suffices to bring about a well-defined change in the large-scale hereditary characteristics of the organism. These facts are easily the most interesting that science has revealed in our day. We may be inclined to find them, after all, not wholly unacceptable. An organism's astonishing gift of concentrating a stream of order on itself and thus escaping the decay into atomic chaos, of drinking orderliness from a suitable environment, seems to be connected with the presence of the aperiodic solids, the chromosome molecules, which doubtless represent the highest degree of well-ordered atomic association we know of, much higher than the ordinary periodic crystal, in virtue of the individual role every atom and every radical is playing here. To put it briefly, we witness the event that existing order displays the power of maintaining itself and of producing orderly events. That sounds plausible enough, though in finding it plausible we, no doubt, draw on experience concerning social organization and other events which involve the activity of organisms. And so it might seem that something like a vicious cycle is implied. Summarizing the physical situation. However that may be, the point to emphasize again and again is that to the physicist, the state of affairs is not only not plausible, but most exciting, because it is unprecedented. Contrary to common belief, the regular course of events, governed by the laws of physics, is never the consequence of one well-ordered configuration of atoms, not unless that configuration of atoms repeats itself a great number of times, either as in the periodic crystal, or as in a liquid, or in a gas composed of a great number of identical molecules. Even when the chemist handles a very complicated molecule in vivo, he is always faced with an enormous number of like molecules. To them, his laws apply. He might tell you, for example, that 1 minute after he has started some particular reaction, half of the molecules will have reacted, and after a second minute, 3/4 of them will have done so. But whether any particular molecule, supposing you could follow its course, will be among those which have reacted or among those which are still untouched, he could not predict. That is a matter of pure chance. This is not a purely theoretical conjecture. It is not that we can never observe the fate of a single small group of atoms, or even of a single atom. We can, occasionally. But whenever we do, we find complete irregularity, cooperating to produce regularity only on the average. We have dealt with an example in Chapter 1. The Brownian movement of a small particle suspended in a liquid is completely irregular. But if there are many similar particles, they will, by their irregular movement, give rise to the regular phenomenon of diffusion. The disintegration of a small radioactive atom is observable. It emits a projectile which causes a small, visible scintillation on a fluorescent screen. But if you are given a single radioactive atom, its probable lifetime is much less certain than that of a healthy sparrow. Indeed, nothing more can be said about it than this. As long as it lives, and that may be for thousands of years, the chance of its blowing up within the next second, whether large or small, remains the same. This patent lack of individual determination, nevertheless, results in the exact exponential law of decay of a large number of radioactive atoms of the same kind. The striking contrast. In biology, we are faced with an entirely different situation. A single group of atoms, existing only in one copy, produces orderly events, marvelously tuned in with each other, and with the environment according to most subtle laws. I said, existing only in one copy, for after all, we have the example of the egg and of the unicellular organism. In the following stages of a higher organism, the copies are multiplied, that is true. But to what extent? Something like 10 to the power of 14 in a grown mammal, I understand. What is that? Only a millionth of the number of molecules in 1 cubic inch of air, though comparatively bulky. By coalescing, they would form but a tiny drop of liquid. And look at the way they are actually distributed. Every cell harbors just one of them, or two, if we bear in mind diploidy. Since we know the power this tiny central office has in the isolated cell, do they not resemble stations of local government dispersed through the body, communicating with each other with great ease, thanks to the code that is common to all of them? Well, that is a fantastic description, perhaps less becoming a scientist than a poet. However, it needs no poetical imagination, but only clear and sober scientific reflection to recognize that we are here obviously faced with events whose regular and lawful unfolding is guided by a mechanism entirely different from the probability mechanism of physics. For it is simply a fact of observation that the guiding principle in every cell is embodied in a single atomic association, existing only in one copy, or sometimes two, and a fact of observation that it results in producing events which are a paragon of orderliness. Whether we find it astonishing, or whether we find it quite plausible, that a small but highly organized group of atoms be capable of acting in this manner, the situation is unprecedented. It is unknown anywhere else except in living matter. The physicist and the chemist, investigating inanimate matter, have never witnessed phenomena which they had to interpret in this way. The case did not arise, and so our theory does not cover it. Our beautiful statistical theory, of which we were so justly proud because it allowed us to look behind the curtain, to watch the magnificent order of exact physical law coming forth from atomic and molecular disorder, because it revealed that the most important, the most general, the all-embracing law of entropy, increase, could be understood without a special assumption ad hoc, for it is nothing but molecular disorder itself. 2 ways of producing orderliness. The orderliness encountered in the unfolding of life springs from a different source. It appears that there are 2 different mechanisms by which orderly events can be produced. The statistical mechanism, which produces order from disorder, and the new one, producing order from order. To the unprejudiced mind, the second principle appears to be much simpler, much more plausible. No doubt, it is. That is why physicists were so proud to have fallen in with the other one, the order from disorder principle, which is actually followed in nature and which alone conveys an understanding of the great line of natural events, in the first place of their irreversibility. But we cannot expect that the laws of physics derived from it suffice straight away to explain the behavior of a living matter, whose most striking features are visibly based to a large extent on the order from disorder principle. You would not expect two entirely different mechanisms to bring about the same type of law. You would not expect your latchkey to open your neighbor's door as well. We must therefore not be discouraged by the difficulty of interpreting life by the ordinary laws of physics, for that is just what is to be expected from the knowledge we have gained of the structure of living matter. We must be prepared to find a new type of physical law prevailing in it. Or are we to term it a non-physical, not to say superphysical law? The new principle is not alien to physics. No, I do not think that. For the new principle that is involved is a genuinely physical one. It is, in my opinion, nothing else than the principle of quantum theory over again. To explain this, we have to go to some length, including a refinement, not to say an amendment, of the assertion previously made, namely, that all physical laws are based on statistics. This assertion, made again and again, could not fail to arouse contradiction. For, indeed, there are phenomena whose conspicuous features are visibly based directly on the order from order principle and appear to have nothing to do with statistics or molecular disorder. The order of the solar system, the motion of the planets, is maintained for an almost indefinite time. The constellation of this moment is directly connected with the constellation at any particular moment in the times of the pyramids. It can be traced back to it, or vice versa. Historical eclipses have been calculated and have been found in close agreement with historical records, or have even in some cases served to correct the accepted chronology. These calculations do not imply any statistics. They are based solely on Newton's law of universal attraction. Nor does the regular motion of a good clock or of any similar mechanism appear to have anything to do with statistics. In short, all purely mechanical events seem to follow distinctly and directly from the order from order principle. And if we say mechanical, the term must be taken in a wide sense. A very useful kind of clock is, as you know, based on the regular transmission of electric pulses from the power station. I remember an interesting little paper by Max Planck on the topic, the dynamical and the statistical type of law. The distinction is precisely the one we have here labeled as order from order and order from disorder. The object of that paper was to show how the interesting statistical type of law, controlling large-scale events, is constituted from the dynamical laws supposed to govern the small-scale events, the interaction of the single atoms and molecules. The latter is illustrated by the large-scale mechanical phenomena, as the motion of the planets or of a clock, etc. Thus it would appear that the new principle, the order from order principle, to which we have pointed with great solemnity as the real clue to the understanding of life, is not at all new to physics. Planck's attitude even vindicates priority for it. We seem to arrive at the ridiculous conclusion that the clue to the understanding of life is that it is based on a pure mechanism, a clockwork in the sense of Planck's paper. The conclusion is not ridiculous and is, in my opinion, not entirely wrong, but it has to be taken with a very big grain of salt. The motion of a clock. Let us analyze the motion of a real clock accurately. It is not at all a purely mechanical phenomenon. A purely mechanical clock would need no spring, no winding. Once set in motion, it would go on forever. A real clock without a spring stops after a few beats of the pendulum. Its mechanical energy is turned into heat. This is an infinitely complicated, atomistic process. The general picture the physicist forms of it compels him to admit that the inverse process is not entirely impossible. A springless clock might suddenly begin to move at the expense of the heat energy of its own cogwheels and of the environment. The physicist would have to say, the clock experiences an exceptionally intense fit of Brownian movement. We have seen in Chapter 2, page 16, that with a very sensitive torsional balance, electrometer or galvanometer, that sort of thing happens all the time. In the case of a clock, it is, of course, infinitely unlikely. Whether the motion of a clock is to be assigned to the dynamical or to the statistical type of lawful events, to use Planck's expressions, depends on our attitude. In calling it a dynamical phenomenon, we fix attention on the regular going that can be secured by a comparatively weak spring, which overcomes the small disturbances by heat motion so that we may disregard them. But if we remember that without a spring, the clock is gradually slowed down by friction, we find that this process can only be understood as a statistical phenomenon. However insignificant the frictional and heating effects in a clock may be from the practical point of view, there can be no doubt that the second attitude, which does not neglect them, is the more fundamental one, even when we are faced with the regular motion of a clock that is driven by a spring. For it must not be believed that the driving mechanism really does away with the statistical nature of the process. The true physical picture includes the possibility that even a regularly going clock should all at once invert its motion and, working backward, rewind its own spring at the expense of the heat of the environment. The event is just still a little less likely than a Brownian fit of a clock without driving mechanism. Clockwork, after all, statistical. Let us now review the situation. The simplest case we have analyzed is representative of many others. In fact, of all such as appear to evade the all-embracing principle of molecular statistics. Clockworks make of real physical matter, in contrast to imagination, are not true clockworks. The element of chance may be more or less reduced. The likelihood of the clock suddenly going altogether wrong may be infinitesimal, but it always remains in the background. Even in the motion of the celestial bodies, irreversible friction and thermal influences are not wanting. Thus, the rotation of the Earth is slowly diminished by tidal friction, and along with this reduction, the Moon gradually recedes from the Earth, which would not happen if the Earth were a completely rigid, rotating sphere. Nevertheless, the fact remains that physical clockworks visibly display very prominent order-from-order features, the type that aroused the physicist's excitement when he encountered them in the organism. It seems likely that the two cases have, after all, something in common. It remains to be seen what this is, and what is the striking difference which makes the case of the organism, after all, novel and unprecedented. Nernst's theorem. When does a physical system, any kind of association of atoms, display dynamical law, in Planck's meaning, or clockwork features? Quantum theory has a very short answer to this question, vis-a-vis at the absolute zero of temperature. As zero temperature is approached, the molecular disorder ceases to have any bearing on physical events. This fact was, by the way, not discovered by theory, but by carefully investigating chemical reactions over a wide range of temperatures and extrapolating the results to zero temperature, which cannot actually be reached. This is Walter Nernst's famous heat theorem, which is sometimes, and not unduly, given the proud name of the third law of thermodynamics, the first being the energy principle, the second being the entropy principle. Quantum theory provides the rational foundation of Nernst's empirical law, and also enables us to estimate how closely a system must approach to the absolute zero in order to display an approximately dynamical behavior. What temperature is in any particular case already practically equivalent to zero? Now, you must not believe that this always has to be a very low temperature. Indeed, Nernst's discovery was induced by the fact that even at room temperature, entropy plays an astonishingly insignificant role in many chemical reactions. Let me recall that entropy is a direct measure of molecular disorder vis-a-vis its logarithm. The pendulum clock is virtually at zero temperature. What about a pendulum clock? For a pendulum clock, room temperature is practically equivalent to zero. That is the reason why it works dynamically. It will continue to work as it does if you cool it, provided that you have removed all traces of oil. But it does not continue to work if you heat it above room temperature, for it will eventually melt. The relation between clockwork and organism. That seems very trivial, but it does, I think, hit the cardinal point. Clockworks are capable of functioning dynamically because they are built of solids, which are kept in shape by London-Heitler forces, strong enough to elude the disorderly tendency of heat motion at ordinary temperature. Now, I think few words more are needed to disclose the point of resemblance between a clockwork and an organism. It is simply and solely that the latter also hinges upon a solid, the aperiodic crystal forming the hereditary substance, largely withdrawn from the disorder of heat motion. But please do not accuse me of calling the chromosome fibers just the cogs of the organic machine, at least not without a reference to the profound physical theories on which the simile is based. For, indeed, it needs still less rhetoric to recall the fundamental difference between the two, and to justify the epithets novel and unprecedented in the biological case. The most striking features are, first, the curious distribution of the cogs in a many-celled organism, for which I may refer to the somewhat poetical description on page 79, and secondly, the fact that the single cog is not, of course, human make, but is the finest masterpiece ever achieved along the lines of the Lord's quantum mechanics.